Last I had talked to you about how to go about finding out the latitude by meridian altitude, and I had talked about three possibilities when the latitude declination had the same name, declination was more, less, or opposite names, and we came to the conclusion that the latitude can be found out by finding out the zenith distance and declination. Now we know how to go about calculating our altitude, sextant altitude, applying various corrections and getting my zenith distance. Now the next thing is to find out the declination. What is required here? Now to find out our declination, we require the time. Now the time is kept with an imaginary body which is called mean sun, and that is how we talk about Greenwich Mean Time and local mean time. What exactly is mean sun and other things I'll be talking to you in detail once we get into the topic of time. For the time being, just a little bit what you should know how to convert your longitude to longitude to time or time into longitudes. So I'll just briefly talk about the relation between the longitudes and the time. A mean solar day is of 24 hours, and it is considered that the mean sun will transit the same meridian twice. That successive transit is a mean solar day, and that we take it as 24 hours. Now, 24 hours in the Earth goes around in 24 hours of mean solar time, so it covers up 15 degree per hour. And thus the relationship between the longitude and the time comes up something like this, that 15 degrees of arc of longitude is 1 hour, and then 1 degree would be 4 minutes, and then 1 minute of longitude would be 1 second, and so on. This is required so that you are able to convert your time into the longitudes or longitude into time. Now to convert, we have conversion tables given in our nautical almanacs. Just tell you how to go about using it. I've just taken an example of longitude 130 degrees 27 minutes. These tables, you have the degrees here and hours and minutes here. 130 degrees is here, 8 hours 40 minutes. Now adjoining table here has got minutes, so 27 minutes, and look for 27 minutes here. And 27 minutes is minutes and seconds, 1 minute 48 seconds. So this is how we go about converting our longitude into time. Of course, you all have calculators, so with nowadays nobody uses these tables much. So you'll just be doing it with calculators divided by 15, and you get your 8 hours point something multiplied by 60, multiplied by 60, and you get your time. Now, how do you convert this time into longitudes? Similar way, now you look around for 6 hours 8 minutes away, and 6 hours 8 minutes, the closest is coming here, which is of course here 92 degrees 08 minutes. So what is remaining is 40 seconds now. I'll go for 40 seconds here, and that is 40 seconds, 40 minutes of the arc of longitude. So my longitude is 90 degrees, 92 degrees, 10 minutes. This is how you go about converting your uh, longitude to time, time into longitude, which will be required to convert our time or longitude. Now, if the same thing, if you had to do it with the calculator, you multiply the hours by 15, minutes by 15, seconds by 15, and so on, and you get your answer here. Now, a mean solar day is of 24 hours. That's what we talked about. Now, this is your Greenwich Meridian, inferior meridian. We start off our day at midnight, as you all know, and when we talk about uh, Greenwich time, so it will be measured from Greenwich. So when the sun is on the inferior meridian of Greenwich, that is the time the day starts. GMT is westerly hour angle measured from its inferior meridian to the mean sun. If the mean sun is on the inferior meridian, it will be 000 hours. As you can see, it is 90 degrees away. 90 degrees divided by 15. So it will be GMT 06, measured from inferior meridian to the mean sun. Inferior meridian to the mean sun is 180 degrees. It will be GMT 1200 hours. Assuming that an observer is on 45 degrees east, so 45 is 135 degrees from the inferior meridian. 135 divided by 15, 9 hours. So GMT would be 9 hours here. LMT is again measured from the inferior meridian. So all the time is being measured from the inferior meridian. Day for anybody starts off at midnight. Now inferior meridian to 45 degrees, 180 degrees plus 45 would be 135 degrees west. And the angle measured from the inferior meridian to the mean sun is your LMT. And it's 180 degrees opposite. 180 divided by 15, 12 hours. Here you can see that O dash P and M, that is your LMT, is equal to O dash P G dash plus G dash P and M, and G dash P and M is GMT. Now O dash P G dash is equal to this angle here, because this angle we said is 135, the remaining is 45, so this angle and this angle is same. So LMT is become GMT plus longitude east. Taking our observer on the west side, mean sun on the meridian, this is 180 plus 45, that is 12 plus 3, GMT would be 1500 hours. LMT is measured from inferior meridian to the mean sun, 180 degrees, LMT would be 1200 hours. And you can see here that LMT is equal to GMT minus this angle, which is the same as the longitude. So LMT is equal to GMT minus longitude west. This is an important relationship for us to get to what is GMT and what is LMT. Now, time of meridian passage, how do we go about finding it out? In almanac, all the information what is given there is all tabulated against GMT date and GMT time. This is one of the pages of the almanac here. You can see GMT, GMT day and GMT time. For time of meridian passage, for sun, sunrise, sunset, twilight, planets, meridian passage, what is given there, they're all in GMT, but they can be considered as approximate LMT in any longitude without any appreciable error. Will not make much of an error. Of course, with moon, there is some longitude correction which we'll be dealing a bit later. So today I'll not be talking to you about moon or stars. Today I'll be just talking to you about sun and planets. Now, just an example here, just to see that how close it is and what the error is. If suppose we are in this longitude, we should be in time zone of 11, and this is the meridian passage time what is given here. On 23rd, the meridian passage time is 11:52. Longitude and time So the sun would be on the meridian, on this meridian, 10 hours earlier, GMT. So this would be the GMT when the sun is on the meridian of this. If I apply this my zone time here, which is my zone is 11 hours, my zone time would be 12 hours 04 minutes, and it's quite close. So that is why I said that you can take it as approximate LMT. Similarly, just showing you for planet here. Again, the meridian passage times are given on the thing which are of course in GMT taken as LMT. Jupiter 1141, longitude and time. So Jupiter would be on my meridian 10 hours earlier. So this would be the GMT and it is on our meridian. Applying my zone time here 11 zone. I was in the zone of 11. So the time here is 11:53. Minus zone means plus you have to add it up and you get your zone time, and you can see that it's quite close. So no harm in taking whatever times are given as LMT. This is one of the pages of the almanac here. Meridian passage times are given here at the bottom. So today I'm not talking about moon or equation of time, which will be dealt a bit later. If you look at the thing here, to find out a declination, which is declination is given here. Declination, I require the time, so I should have my GMT time. Now below the declination, if you notice, or along with the declination here for moon, under sun D, along the various planets you have D. This D correction is to be applied to the declination whatever is given here, because whenever we take our altitude, it will not be a full angle, it will be some fraction. So we'll have to interpolate between whatever the time we have got. It will not be an exact hour. So this D is the change in declination in 1 hour. If you notice here, 51.8, 51.3, the difference is 0.5. Similarly, you'll notice here also that the difference is 0.1. Somewhere here, 0. So this difference is what the change of declination is there in 1 hour. And now we require for the fraction of time, but we get the correction in our increment tables. Now it has to be added or subtracted, has to be decided by looking at your declination here. As we can see that my declination here is reducing. Similarly here, if you look at it here, 23.924, it is increasing. So if it is reducing, the D correction is minus, and if it is increasing, the D correction becomes positive. Now here I have come up with positive and negative sign here. You can see that here it is reducing, so the D correction will be minus, and here you can see the declination is increasing, so the D correction would be plus. Then below here we saw that along with D, V was given, and V is given for all the planets, and for moon it is given hourly, for rest of them is given for 3 days, and there is no V correction for Aries. Now this is just, we assume that the GHA of Sun, planets and Aries are increasing by the amount of 15 degrees of 15 degrees 02.5, and for moon 14 degrees 09. This GHA increases this amount. It is never less than this. It can be more than this. So that the amount what it is changing in 1 hour instead of that 15 degrees or 15 degrees 0, 2.5 or whatever I have taken. That is what the V correction is. If you look at it here, the difference between this, it is not exactly 15. There is a difference of about 2.6, what is mentioned here. It is so we will, that is the V correction, an hourly change in the GHA. For fraction of it, we'll have to visit the increment tables. So these are the two important corrections what you have to apply for declination and the GHA. Now, how do we go about finding out a time for meridian passage? As I said, for 1st September, longitude is given to me. Meridian passage time is 1200 hours. This is the approximate time. And I change my longitude and time, and then I have this here. So this was my approximate LMT, and this is my GMT. LMT is equal to GMT plus minus east-west longitude. It is east here. And we got a GMT. Now if I had to find out my LHA for this particular time, how do I go about doing it? I go to the particular page of 1st September, 08 hours, 300, 01, and my declination, 8 degrees 0, 8.8. So I wrote down my DHA and my declination. And below the declination it is 9. And here I can see that the values are reducing. You can see from 8 it has come to 7. So minus. Now I have still got this fraction of an hour here. So I go to my increment tables for 38, 12, and I get my increment for 38 minutes 12 seconds from here, 9 degrees 33 minutes. In the same table we have V and D correction here. D correction was 0.9. I look for 0.9 here, and the correction is 0.6. I apply 0.6 here, minus, and this is my declination. This is how I calculate my declination. Then I add my increment, get my GHA, sun, longitude. Now here, there is no V correction, so I have not bothered about V correction. Whereas for, as I told you, for moon and other planets, we have V correction. And sun, there is no V correction because whatever the difference over and above 15 is adjusted over the period of time in these pages. So there is no V correction for sun. And this is my LHA. When the body is on my meridian, we know that the LHA is the angle at the poles. When it is on the meridian, there is no angle. So the LHA is 360 or 000 when the body is on your meridian. So now if I was asked to find out the exact time, so what I will do is I will start from reversed. I'll take the LHA is 360, apply my longitude, and I'll get my GHA. And then now you can see that there is a slight difference between the GHA what I have calculated using the approximate time and this. Then I look around for this value for GHA which is slightly less than the GHA what I have calculated. So I go to the page of 1st September here and I look for a value which is less than 309 degrees. Now you can see from 309 the closest is 300. 315 is more. We could have done it with the 315, but that is not a regular practice what are shown in the books here. Maybe I'll talk about it when I'm talking about stars. So I look for the lower value and I come to the value of a lower value of GHA as 300 and 0.1, which is for 8 hours. The difference between what I have got here and this value, that is the increment, which I should be adding up, and that's how I'll get this value, right? And then I go to the increment tables to find out when this increment, what minutes and seconds it will be, and as I can see here in 38 and 08, I can see that the increment is 9:32. So my exact time of meridian passage would be 8 hours 38 minutes 08 seconds. Now we assume that the date what I have taken into account is the same date for GMT, but it may differ. So it will be always advisable to check that the GMT what we have calculated for the date is correct to our LMT. So I've got the GMT. I use my LIT here and LMT, GMT plus minus waste, and yes, there is no change of date. So this is perfectly okay. Just an example of a planet here. Again, when I look into my almanac for that particular date, I get the date here, time 1936, and this is the approximate LMT. I use my LIT and I get my GMT using this formula here. And if I had to calculate my LHA now, I'll go into the same date, third, 2300 hours, Jupiter, 5006.6, and my declination is given here. I have not entered the declination here because I know that the date is changing, but so that's why I have not bothered to enter this. So I've just taken the GHA here. At the bottom, I have V correction 2.4. So I entered V correction here 2.4. That is required. Then I go to my increment tables for 58 minutes. See here 00 seconds. So my increment for Sun planet is 14 degrees 0 30 minutes. And my V correction is 2.4. I look for 2.4 here, and the correction is 2.3. And as I said, V correction is always positive, except in case of Venus. So this GHA what I have calculated here is with the increment for 58 minutes plus the V correction, and that's my final GHA. Then to get my LHA, I have to use this formula. LHA is equal to GHA plus minus east-west longitude. I've got to subtract here, so I cannot subtract. That's why I have just left the space here, added 360, and this is my LHA. As I had said that when the body is on your meridian, the LHA should be 360. So here you can see that it's not exactly 360. So this is an approximate time of meridian passage. But if you are asked to find out exact time of meridian passage, you would start off with LHA as 360. You'll apply a longitude and you are going reverse. And of course, there is a change of GHA here because the values have changed. We have got the GHA. So this is the GHA when the body was on my meridian. Now this GHA, as you can see here, is the sum total of the increment for the fraction of an hour plus V correction. So V correction is already there added into this. So if I have to come to this value of GHA, I have to subtract the V correction because it was added when I was going down. Now I'm going the reverse. It has to be subtracted. So I go to the same page of third and look for a value of GHA which is less than 65, and I get the value here, 50 degrees. This is your Jupiter. I go for the value here, 64 degrees, 10.3. So I have taken the hour value here. Now the difference between this and this is the increment, which includes the V correction. So what is the increment here now? 1 degree, 19.7. And now in this the V correction is also added. So I have to subtract the V correction from this value. The V correction was 2.4. This increment, I look in the increment table, this increment is in 5 minutes. In 5 minutes here, somewhere here. And the V correction of 2.4.2, I will, now I have to subtract it from the total increment here. And this is the increment what I get, 19.5, which is for 5 minutes and 18 seconds. So this is my exact time for meridian passage of Jupiter on 3rd. Now, as I said, we assume that the date is the same. So I will check up the date if the date is correct. So I use my GMT, my longitude and time. I have not done the full calculation. You will have to do the full calculations here to show it. And I find that after applying my LIT, the LMT changes to second. Now the date on the ship has to be correct. That means the time what I have looked for the GMT is wrong. So I should be looking for 4th. Then only I'll get my LMT as 3rd. So once a situation like this comes up, we will have to redo this whole thing again for the date of 4th. If this was a case of sun, subtracting 24 degrees or adding 24 hours would suffice. But for planets, you'll have to redo this whole thing again. So just redoing it again for 4th. So up to GHA is right. It's the same thing up to GHA. Now I go to the date for 4th, and when I go for the date for 4th, I get my GHA next less GHA less than this as 6509, and my declination. Now I'm writing down my declination because the date has changed. I knew that, and that is my declination. And the D correction here is 0, so there is no correction for D. That will be my declination. If there was D correction, then I would have to go into the increment tables to find out D. Now this GHA, the difference between this and this, whatever the increment is, has got the V correction for this added up. So I go into the increment tables to look around where this increment is, and that is 1 minute. You can see 21 is here. So this increment is for 1 minute. I get the V correction 2.4, which is 0.1. As I said, this increment was already including this, so I'll subtract it from here, and I would get my correct increment would be 00 degrees, 20.9. Now I look for 20.9 here, which is 24 seconds. So my correct time would be 1 minute, 24 seconds. So this is how we find out our time for meridian passage. Now this change of date can be understood or can be found out much earlier than doing all this thing what we have done. But for you, you'll have to show this part of it. First calculate it for the day concerned, and then if you find the date changing, then you'll have to restart with this. But you can make out if the date is changing or not by looking at your almanac. Now, the all the celestial bodies, the movement is from east to west. You have your Greenwich here, and east longitude, west longitude, and bodies move from east to west. when the body is on Greenwich, then the GHA would be of a particular body would be 0, because Greenwich GHA is what angle at pole between Greenwich and the body. When the body is on the Greenwich, GHA would be 0. Now the date given to me was the third. On third, I just look at it when the GHA is 0. And when I look at this table here, the GHA is 0 somewhere between 19 and 20 hours, somewhere here. So at Greenwich, the body would come on its meridian between 19 and 20 hours. So, and onto the west, definitely it has to come later. It is going to come later. It cannot be earlier. So I should have been looking around for this value of GHA, lesser value of GHA, not before this time, but after this time. If it was question of east, yes, then this would have been okay. But west, because the body will be coming on its meridian after GMT, after it is on the meridian of Greenwich, when the GHA would be 0. So I should have been looking at the date below. So this is an easier way to find out change of dates. So as I said, for you, for the examination part of it, you'll have to show the calculations here. But you can always make out if the date is changing or not, and you can be aware of it in advance. Thank you very much. Would continue from where we left.